Thank you. So, how is it with the break? You said something with no.
Yeah, without break.
Without. Okay. So let me start with the meeting of what we just made about yesterday or close to that. We discussed how does the chair number come about for complex vector bundles on the two cores, and we quickly call the answer because we something similar today. So we have the two topes that was cut out to cylinder, and then we had the frames over each point that is basis in the vector space, which is the fiber of the bundle of the point. And over, so this point is a duplication of the point over there, just separated by the cloud. But the frames we have here, the frame we have there, are not necessarily the same, and they are related by a matrix that depends on the coordinates by along the top. The cut is a circle, and as this coordinate phi 2 runs along the circle, this matrix T phi 2, T of phi 2 runs a circle in GLM, and as such, also the determinant of that matrix runs a circle in the complex plane that avoids the origin, and as such, it has a winding number, and that is one way of expressing the Chern number of the vector bundle on which we start. Okay, and then the picture that comes with it is that you can look at the eigenvalues, little t of phi 2 for any such transition matrix, capital T of phi 2. Look at the phases as phi 2 runs along the circle, and then you get the picture like this, with phi 2 equals 0 at the left end, phi 2 equals 2 pi at the right end, and as a result, these phases coming from this matrix, which comes back to itself, also come back to themselves. So they are drawn at the same position along the circle. But in between, they may wander and wind around this cylinder. And you can count that winding by drawing a fiducial line like the red one there and counting the crossings. And there are taking the sign into account, 2 or minus 2. In fact, minus 2 should take into account the properly the sign. So that's how the Chern number was obtained for vector bonds that have no symmetry attached to it. And then we went on to time reversal invariant topological insulators, and let me see whether we can jump here. Okay. So we just go 1 or 2 back here. Right. So on top of what we had before, a symmetry is added. So we have an insulator as before. There is a gap between the bands where we put the Fermi energy. But in addition, there is a mass theta on the Hilbert space that's called the time reversal. It is anti-unit squares to -1. And it commutes with the Hamilton. And then we have the Hamiltonian that fibers for each value of the quasi-momentum of h of k. And when you conjugate h of k with time reversal, so the fact that as a whole would go back to h, 5 by 5, that is quasi-momentum by quasi-momentum, goes to the opposite quasi. So in particular, also the map theta is a map that goes from the fiber over k to the fiber of opposite quasi-momentum lines. Okay, and then we saw that the Chern number of such vector bundle that have this symmetry on top is 3, so it is 0. And so there is no obstruction of there being a global frame that is over each point. You have a basis in the vector space that is the fiber, and it runs smoothly all over those loops include. Okay, and then so this is just from the previous slide, and okay, and then you can ask how do you classify those objects, and they can be classified by an index, which takes the values plus or minus 1, or and the choice is 0 or 1, but let's use the multiplicative notation. And if it's plus 1, that corresponds to the identity element, this multiplicative group of two elements, then it's the ordinary insulator. If it's not the identity, the group, then they put something more fancy, and it's the topology. So they came with me, and they came, realized these indexes of Grafin. They would like to show how this comes about. So there you go. You see again the two poles with points called phi other than k. So about that, the coordinates are phi1 and phi2. This is depicted as a square, but opposite sides are blue. And what is now important, that with any point phi, the opposite point minus phi plays a distinguished role. Now you see that there are some points that are equal to their opposite. Like the point here, the origin is coordinates by 1, 2, 0, 0. That is mapped to itself, but it's not the only one. Take this one, where you would say this goes over there, but we being on the torus, that's the same point. And likewise, there is one, which is the same as the point down there. And also this point on the corner is actually the same as the other, as the point on the other three corners, because they are all the same on this inversion map, I goes to minus 5. Okay, and then like once last time that they called the theta maps. So maps the base point phi to minus 5, but along with it, the fiber over it, and gives this map, which is anti-linear, it's close to minus 1. And then we want to construct again frames. So over in each d phi, we choose a basis, and would like to do it as globally as possible. But not just as that we know we can, because there is no obstruction which are under our zero. But we would like to choose this basis in a way that is suited to the symmetry we now have. So the choice of basis of phi should bear some relation to the choice of basis over minus phi. And maybe I don't need to go just the last sentence. No, I will skip that. In any event, let me tell you about full Kelvin. So they assume that there is an inner product on the fiber. That's perfect. It's not being quantum mechanics. And given that there is that the Chern number is 0, there is no obstruction for having a global section. And now don't just take any global section. Do not ask for it having particular properties because of the symmetry. And then you can construct this matrix here, W is n plus ij, and you can construct it for every point on the box. And it goes like this. So you look at the j's vector at point minus phi, and then you apply theta. That will give you some vector in the fiber over phi, because theta maps the fiber over minus phi to the fiber over phi. And there you have another vector. Getting confused with this. Then you have another vector ui of phi from the basis that sits at e phi. And so you can build this matrix because these two are vectors in the same files. Now, the uj that came from minus phi are still linearly independent when you map this theta. And this is anyway a basis. So this matrix here is a change of basis matrix, and in particular, it is invertible, and in fact, if this fuse had been chosen orthonormal, it is unique. And another property that has to do with the fact that theta squares to minus 1, it's not difficult to see here, is that if you take the transpose of this matrix at any phi, you get up to a minus sign in front, that matrix at the opposite point minus phi. So it is in general not anti-symmetric. Transpose is not minus itself, except at this time reversal invariant points. I'm not sure I said what I said, right? This point should be called time reversal invariant. No, it says time reversal trips. Okay, a trips, this matrix is anti-symmetric. And so what they did is this. You should know that anti-symmetric matrices have a path, and I will explain it in a second. So that's a number, and it is one of the two possible square roots of the determinant. And there is one more thing that could be said, so that the determinant never vanishes across the whole corpus because of this relation here. And so at each point you have two values. So the square root of the determinant that comes up here is slightly ambiguous because you don't quite know which square root to take. But at each point, the two are distinct. And it so happens that if you take one branch and you go all over the toes, loop included, you come back to the same branch. I'm not going to explain that, but you can take one branch once and for all over the whole groups. But as for the Pfaffian, you can compute it only at discrete points, because only there the matrix is anti-symmetric. And so at these points, you compute this quotient, which is a number that's plus or minus 1. And you multiply this, and then you get finally a number that is also plus or minus 1. And that is going to be the index. So as a time reversal invariant bundle, this bundle is trivial if the index is plus 1, so yes, and it is non-trivial if the index is minus. And I checked whether this has anything to do with the solid transform. I don't think so, but we can talk about it. So I'm not sure whether I should say what the Pfaffian is. So if you have an anti-symmetric matrix of even order, so it is unnecessary. So no, it's not necessary, but only if it's of even order, the Pfaffian is interesting. Then you can take your indices and pair them in many ways, and each pairing defines a permutation. And then the Pfaffian of that matrix A is defined by this. So the pairings are called pi. You take the signature of that for the corresponding permutation that you see here. You multiply A, I1, J1, and so on. So it resembles a little bit the determinant. Let me just go to this remark. Not to be confused with the determinant of a matrix, but you sum over all permutations, but you do this construction, and to understand the difference, let's just look at one simple example. A 2x2 matrix that is anti-symmetric. The Pfaffian of that one, well, what is it? You would do one pairing of the indices, and there are not that many, 1, 2, and so you just take the index, the element of index 1, 2, and that is A, and that is the Pfaffian. Whereas with the determinant, you know how you do it, you pick one, always pushing the wrong thing. Determinant is that. So it's not the same thing, but the determinant is the square of the Pfaffian, and that is what we have been using before. So, let me move on here for just a little while to explain that there is another way of expressing this index that we found with Marcello Porta. And let me not give all the details, it would take possibly too long. I would like to make sure that we can cover another chapter. So here's a picture like the one I just showed when starting again. But it's slightly different, as you may know. So the configuration you have at the initial circuit is not the configuration you have at the final circuit. They don't have to be the same. So there's one condition less in this regard, but there's one condition more in that you have a pairing at the at the beginning, so they have to pair up at the beginning and pair up at the end. And so you can say that you have so call T the parameter that runs along this axis of the circle. You have a collection of the points, a collection of points on the circle that depends on. And what we like to do is to deform such collections, including at the endpoints. And what I claim is that not any two collections that you may come up with can be formed into one another. They come in two distinct classes. And here is how these distinct classes come about. What is the index that tells the difference between the two? Well, you draw again a fiducial line, and here you get the winding number of three crossings. You know, you might change this when it gets to be 5 crossings. You see, there is no reason for this number to remain the same, even if you count the sign of the crossing, because if you move this fiducial line such that you just pass one of these final points, but nothing happens on the other one because they are not necessarily at the same height, then you lose 2 crossings. Before, you wouldn't have lost 2 crossings because this point would have had to be at the same height at that point. So what you would have gained at one end, you would have lost, you would have gained blocking from the other one. But now this can change. So it can be 5. In this case, you just see it's 1. But what you may start notice is that the parity of that number hasn't changed. So the parity of the number of crossings of this fiducial line is the index of this family of this collection of points of this picture. And now, what has this got to do with the problem of the index? Well, let me be very sketchy because I would like to move on to the next thing. But you remember how we did it with the quantum Hall effect. We took a base on the 2 topos, and we had to glue the choices of bases at the end or try to, and that would have led us to something like this. And now we do something similar again. We'll do something similar again, but we would be careful in choosing the bases in such a way that they are compatible with C. And after some talking, you would end up with such pictures like this, based on which you can identify the index. So it's again, this parity is again something that you do call plus or minus 1, and this is the same as the part index that full K came out. If that's fine with you, I could keep more detailed, but if that's fine with you, I would like to come to the last class I want to discuss, and that is class D or Majorana further. Without here. Now, okay, and now the other one. Okay, and how do we get to the screen again? Okay. This page 1. So it says class D there on the title. And the Kitaev chain and Majorana film. So I hope that people from Naples in the audience and so on would be appropriate to say something about Majorana. So class D is a symmetrically protected topological class. And the symmetry is not time reversal invariance this time, but this particle-hole conjugation sigma. And so the particle-hole is a symmetry that does not commute with the Hamiltonian before, but does anti-commutes with it. So that's the relation here. And it's supposed to be even, so it's sigma squared is equal to plus 1. And if you were to consult the table I showed you before, you would see that it equals 1 the index of this C2. I'm not going to explain that, it will come up in some other way. So, and what is a concrete model? Well, there's a concrete theoretical model, which is the Kitaev chain. And it has been claimed that it could be a good model to implement a qubit. And if this qubit would be realized concretely by the following device here. So you have a superconductor, and on top of that, you place a one-dimensional semiconductor, if you try this in the continuum. And this induces some superconductivity in this one-dimensional object. In one dimension per se, there wouldn't be any superconductivity, but it's being induced by three-dimensional objects underneath. And this red system then can be, it become a superconductor itself, but more than that, it can be topological. And so, in order to explain these things, the first thing is how to describe superconductors. And I hope you had some exposition to second quantization. I will just say the basic, but well, possibly it's not understandable if you understood, heard second quantization before. And I would like to speak of the mean field formulation of superconductivity, in particular the loop of the J-pen. So given a one-particle input space, it should be called H. Then there is a standard construction that associates with a Fock space, particularly a fermionic Fock space. And the state, that's another input space, and the states called psi in this fermionic Fock space are n-particle states, and value of n is not fixed anymore. So in the original input space, that's just one particle. But now it can be 0, 1, and so on. And so these correspond to different subspaces of the Fock space, and particularly in the subspace with anything 0, there's just one unique state of the base called the vacuum corresponds to it. And then, if the original one particle input space H was equipped with some orthonormal basis EI, so index and capital I, then you can associate to each of these basis vectors two operators called the annihilation and the creation of Ci and Ci star. Their meaning, it's as follows. So first, it's a map of the Fock space to itself, sends psi to Ci psi. It's just this in the notation, and that removes a particle. That removes a particle from the state psi, in fact, one in the one particle state ER. And if you try to do this exercise on the vacuum, well, then you will get C. So in particular, to be clear, the vacuum is one state, it's not zero. But when you apply, try to annihilate something from the vacuum where there is nothing, then you don't get another honest vector again, and you get oppositely for the creation operator with Ci star, which is the adjoint of C. Okay. Now, these operators, annihilation and creation operators, they satisfy a certain algebra, the canonical anti-commutation algebra using. So the anti-commute is among them, among operators of the same type, the annihilation or creation operators, but they have this peculiar anti-commutation relation in opposite. In particular, I'm not going to explain that any further, except for noticing that if you apply Ci twice, then by the relation just here, this gives 0. And likewise, if you do Ci star twice, you get 0. And that just expresses it, not possible to move or to add to place two particles in the same state. This being against Paul's exclusion. Now, there is the Barton-Cooper shift theory of superconductivity, which I'm not going to explain. But as an outgrowth, it comes up with a simplified description, which is so-called mean field Hamiltonian. And the whole Hamiltonian is a sum of terms that are bilinear in the creation and annihilation operator. And to write down what these building blocks are, let me say that they are built on matrices A, E, and C. So A, E, and B tilde. Here. And one possible bilinear is C star AC. It's just a compact notation for a double sum of Ci star Aij. We're using the matrix, say, Cj. And likewise, you can construct something with the B, but in this case, you use Ci and Cj, no creation operators. And here you just use the creation. Now, here we decided to put the creation operator on the left rather on the right. But that is somewhat conventional. Here you see what we could do. First, the Aij are just numbers that we could place on the far left. So the creation and annihilation operator just me. But we could flip their position using the anti-commutation relation up there and get this. And so we could flip the position to see, in this case, the I and the I were adjacent. In this case, the J is not adjacent to J, which involves some kind of transposition. A minus sign in front and the shift by this number AI. It's easier when you do it with the piece, where we just get the minus sign and also this transposition, and likewise with the indices. Look here above the red line, you just see some smaller fonts what we had on the previous slide. And here it's summarized what you get. So if you sum this over all I and j, then you get this expression here. And then you sum all this A by I that gives the trace of A, and there you get it in the other order, and this is that position I have. And likewise for the other ones. So these things will come up in the n-body Hamiltonian, the Hamiltonian that acts on the Fock space. And this is just a multiple of the identity. So it's just a shift, omitting it, it's just shifting up or down the Hamiltonian by an additive constant. This is without consequences that can be done. So we omit that, or rather assume that the matrix A uses traces. And there is still this ambiguity. There's still this ambiguity between this writing and the other writing, and we'll resolve it just by taking one half of each. And what you see from here is that only the antisymmetric part of B matters. And so we can just retain that one and drop the symmetric part of it. So the many-body Hamiltonian, this is bilinear based on these building blocks here. So it's one half of the blue terms. So this is the same as this. And we take one half here, it's one half there. And likewise with the other one. And there is one way to rewrite this in this triple group of the Gen formalism, where you put the C daggers and C next to one another. And this becomes a block matrix like this, which is called the triple of the Gen Hamiltonian. And just using the notation that is usually used with psi and deltas, but these are basically things that we already have there. So psi is A, and the delta is not quite the B, but only the antisymmetric part of B matters anyway, so that's the part we entail. And the D tilde is the antisymmetric part of the tilde. And the fact that we use this and the other one that sensitizes are in the other order. The other order is corresponds to the matrix element down here. It's not psi, but minus psi transverse. So that is the formulation you have. And you see that these blocks have constraints among each other. So this thing here is anti-symmetric, and we keep notice of that by placing it here. And also two matrix elements here on the block are related, as I said. Likewise, the T tilde is not free of constant. So this I don't have to repeat because you see it from the block, but you don't see the property of the delta and the delta tilde. So I have to repeat it down there, and it's the reflection of the fairness distance. Okay, sorry about that. So now, however, H, this Hamiltonian H, will also have to be Hermitian. So first, let's not assume that, but just let's find out what it means to pass from H to its adjoint. What does it induce on the Bogoliubov, the Hamiltonian little H? So to do this process on the A, capital H, this implies two things, that you get the C star and the C there. So this means some transposition among blocks, but also the star itself, it means adjunction within blocks. And so if you do these two operations on little h, so adjunction within the blocks, but also transposition between the blocks, the delta ends down there and the delta tilde ends down there. And if this has to be the same, so to have the Bogoliubov-de Gennes Hamiltonian, there is no redundancy in the formulation because we insisted on the anti-symmetry property here. So this has got to be like that. And as a result, we can drop the tilde in favor of the delta tilde in favor of the delta, in fact, delta star. And we retain this constraint from the Ferris that is to say that you get the new one, psi plus psi star, which comes from the Hermitics. It's the formulation for the superconductors in the mean field formula. Now here I'd like to make an example that is at the same time a remark, because I'm telling this. Because I think it brings up a confusing point about this Bogoliubov behavior. So let's make the very simple case where the original Hilbert space, the basic one, is just C, it's one dimension. And therefore, F is just C squared. There's one way not to have that one state and one way to have it that makes for the C squared. Then you have just one set of operators, one operator C and one operator C star. There's no need for an index because this is one dimension. And second quantization generally brings us from 1 to any number of particles, but here just between 0 and 1. And the one particle Hamiltonian, this is just one number, this bigger one-dimensional space. So you pick any fixed energy E and multiply by the identity of this space. And that's the one particle Hilbert space. It has one energy and one state. And then if you look at on the Fock space, you would write this one. So you have two eigenstates, the vacuum, and you add the one particle. And you have two eigenvalues, 0 for the vacuum, and this state E, this energy E for that the only existing one particle. And then we do what we did before. We subtracted half of the place. That's E over 2. And so the eigenvalues, rather than being C and 0 and D, become plus or minus E half. And this is the Bogoliubov, the de Gennes, the little a, Bogoliubov, the de Gennes notation at the Hamiltonian is then E at minus E. And it acts on the doubling of the original Hilbert space, which is now C. So, and it has these eigenvalues plus or minus 1. Of course, here there is also this factor 1/2, which somehow corresponds to the eigenvalues E over 2 that you are supposed to have. So here is the one. Here is a conclusion that is in fact wrong. you could say this thing here looks pretty much like this construction here, and you could say that this capital H is the second quantization of the Pogolub of the Schengen. But if that were so, then the dimension of F would be so what is the dimension of the Fock space if the basic Hilbert space has dimension n? That's 2 to the n. And here that n is 1 plus 1. So the Fock space would have dimension 4. And therefore, H would have a spectrum consisting of 4 elements. And if this has an eigen, if this were really the second quantization, then you could pick none that gives 0. You can pick that one, you can pick that one, you can pick some of them, which is again 0. But that is all wrong. Fock space is 2-dimensional, and you just have, in the Hamiltonian, just has 2 eigenvalues. So the dimension is that, and the H has spectrum just 0 E. So let me, here is the next slide, yes. So more generally, if H is Cn, so I said from F is the dimension of the Fock space C to 2 to the n, because you can, for each state you have here, there are n one, you can choose whether to pick it or not to pick it, which makes this dimension here anyway. And so the Pogolub of the Hamiltonian acts on this direct sum, H plus H, and this does not correspond to the proliferation of physical states, which would give 2 to the 2n if you would pass to the Fock space, but the Fock space has dimension 2 to the n just once. Rather, the eigenvalues of H come in pairs, plus or minus I, these labels, and we should call them modes. And the eigenvalues of H are then, for each of them, you pick them with a plus or minus. In fact, I forgot the 1/2. And this gives 2 to the n states. So the redundancy that you have in this Pogolub of the Jet formalism, you have H plus H instead of just H, is a feature of the formalism mode. So, and when in other words, not each mode gives rise to the corresponding states in the Fock space, but only each pair of eigenvalues for H. In fact, each pair should be considered as a single mode. Not sure it was here, but that's how it goes. So, when looking at the Hamiltonian, at the Pogolub of the Jet Hamiltonian, it has energies and they come as opposite pairs, and each pair is foundational for something in the Fock space, namely the creation or annihilation operator in the Fock space, so a pair of such. Okay, now this Pogolub of the Jet Hamiltonian has a ceiling. How does it go? So here is the Hamiltonian. These are the properties that you have there, and the consequence of the latter one, which you complex conjugate, that you also have the delta complex conjugate is one. So delta adjoint is minus delta complex. And they claim they satisfy a symmetry or an anti-symmetry. H anti-commutes, with sigma, where sigma is even, it's something anti-unitary, consists of the complex conjugation, standard complex conjugation on Cn. And then you have this Pauli matrix or Pauli block matrix that you recognize here. And let me try to give the proof. If you were to compute H sigma, then you would first need the complex conjugation. And that you can pull through. So if it's not yet pulled through, you can pull it through by complex conjugating everything inside the physics. Sigma becomes the psi becomes psi bar, then comes the bar, and then they are already in the transpose complex conjugation. And then once you are there, you still face this Pauli matrix there. And this amounts, you can pull it through if you flip the indices 1 and 2 of both the rows and the columns. if you were to do that, this thing here comes up there, this comes down there, and this comes up here. So, and then you see that this is what you get if you also make use of the symmetry that you know there is. And so you realize that this in this line stage, that now you have both the Pauli matrix on the left and the K on the left. So you go to just this relation. So the conclusion to be drawn here is this. The H is the Bogoliubov and from easy class D because it anti-commutes with an anti-unitary that squares to +1. So and it is so by virtue of the PDG formalism alone, it is not the expression of physical symmetry like time reversal imbalance that we had before. It just comes from the fact that you have a second quantized Hamilton that is bilinear in creation and dilational. That gives that symmetry of phi in the Bogoliubov forms. Nevertheless, topological consequences from that are there, as we shall now see slowly. So now there is this story about Majorana fermions which come up with this class. And it's a little bit of a complicated situation. It's a bit of a misnomer, I think. So the M of Majorana comes up in rather different context. First in particle physics. And what is a Majorana particle? Well, that's a fermionic particle that is identical to its antiparticle. And so if the particle has charge Q, the antiparticle has charge -Q. And if they are identical, well, the charges are the same, which means has no charge. And the candidate for that, who knows whether it's true or not, is the neutrino, and people in the Gran Sasso laboratory on the mountain there, I guess, are probably just another reason why Majorana comes up in this, but related to this one, is that such a Majorana fermion corresponds to a solution of the Dirac equation that is, however, real as opposed to the usual complex valued solution of that equation. And related to this existence of the real solution is that there is a purely imaginary representation of the Clifford algebra. And this is not possible in all space-time dimension, but among those where it is possible, there is 3 + 1, which happens to be ours. Okay. And now it came up, the name came up, and it's now commonplace, also in solid state. It's simple. And one reason for that is perhaps an article that Frank Wilczek wrote, they call Majorana returns. You all know what it is, or what's the pun behind. And so it left, at some point, it was forgotten in particle physics, derived there, but it has made a return to solid state. There, it's more, we should more speak of a Majorana mode, just in the sense of the Bogoliubov the Hamilton I said before. And it's a mode that is identical to its particle Hall conjugate. And as a result, since under particle Hall conjugates here, this antisymmetry I mentioned, energy goes to the minus at the minus section. Here, these two are equal, and therefore such a mode has to have the zero energy. And related to the whole thing is also the Clifford algebra, but not particularly a purely imaginary representation of the Clifford algebra. So, it's not the one-to-one correspondence of the two ways the notion appears in the two sciences. There are some commonalities, but it's not sometimes people get I have to solve it out, I'm not sure. Okay, so here is how we are going to use it. That's a simple thing, but much simpler than Majorana, or Majorana was much deeper than what is now credited for. So let's just talk about canonical anti-commutation relation. So, and the Clifford algebra. That would actually be the more proper name for that. And so just one pair of annihilation and creation operators. So here is the anti-commutation that is satisfied. And the idea is to take the combination of the two, gamma 1, which is Hermitian. So if you take the Hermitian conjugate of that, you get it back. And another combination of two, which is the difference divided by I. So it's gamma 1 and gamma 2. They are both Hermitian. So there you go. And they satisfy other relations that replace those above here, which are called different relations. And there is, and vice versa. If you have gamma 1 and gamma 2 that are Hermitian, so satisfy that, you can write C. So gamma 1 and gamma 2 are just real imaginary part of C. And you can write down the Hermitian conjugate of that gamma 1 minus I 1. And they will satisfy the Goodall canonical anti-commutation. So for later, let me point out this, that C and C star, so as they add one fermion to the system or remove it, they change the parity of the number of fermions. And this combination here, C plus C dagger, also changes the parity. Now C consistently lowered the number of particles by 1. C dagger increased it. So there's no definite change in the number of particles, but the parity is changed. Split. Good. And now let me introduce the type chain. So it's a chain consisting of L sides. And each of L sides poses at most one electron. And so for each side, then J from 1 to L, you have a creation and annihilation operator. And there you write down, or Kitaev wrote down this by now famous Hamiltonian. So you have, I'm commenting each term and it's all one by one as if it were there and O. So you have this thing is known as it counts the particle numbers on the vacuum. It's zero, but if there is one particle already at side J is 1. So the eigenvalues of this round bracket are plus and minus 1. And then it comes with the factor minus mu in 1. So if mu is positive, it favors the occupation. So if mu is positive, it's meaning that the lowest possible energy is the lowest possible energy is if this is large. So if the state is on, mu is negative, it favors it. Then there is another term which removes a particle from one lattice side and moves seeding one, or vice versa, moves it from one and moves it to the successive one. That's nearest neighbor hopping. And then finally you have this term, which is peculiar to superconductivity, because it does not annihilate or create one particle at once. It removes two of them, or places two of them, and what it does, it annihilates, takes a pair of electrons that should be viewed as a Cooper pair. These are the kinds of charge in superconductivity. I cannot give you the field of superconductivity. You have to speak with this. And so the value of the parameters here is that mu and w are real number. System is H. With H being self-adjoint. And here I realized that I made a slight mistake. So delta naught is supposed to be complex, but I should have written the delta naught here and the delta naught complex conjugate in front of this guy. In any event, without loss of generality, that one can do a certain unitary transformation so that delta naught becomes positive. It's like having a point on a circle and you rotate it long enough so that it's on the positive field axis, in half positive field half axis. So that is the model. And let's look at another writing of that. So here you have again the chain, it's L sides, and for each side you have a creation and an annihilation operator. Creation operator is alluded to in brackets with this. And now for each one, so you have two a C and a C dagger here, And as I said before, you can, corresponding to it, you can introduce a gamma 1 and the gamma. The C2 will lead indices gamma 3 and gamma 4. That's how it goes. Gamma 2j minus 1 is Cj plus Cj star, and the next one, gamma 2j, is Cj minus Cj star divided by 1. And no surprise, we also satisfy this Clifford Wheeler system we had before. And if you now translate the writing from before to the depth of Clifford's, you get the Clifford's or Majoranas, other people are saying business. You get this writing. And now I would like to look at two special cases of this model corresponding to two special values of the function. So at the first, so here again, you just have the thing from before. And in the first case, let's take the delta naught, the superconductivity thing, to 0, and also the hopping to 0, and just a mu that favors occupation. So every particle is stuck at the site where it is. There's no way to do anything or to be. And so the Hamiltonian is that one, because only the first term is there, and in the other writing it's that one, also because only the first sums. And so in this case, you see that when you do this, what comes up as a pair in this expression is 2j minus 1 and 2j. So that starts with gamma 1 and gamma. So it's exactly those are pair that come from that same side. No one, right? It's only thing coming from that side that are in the Hamiltonian. There's no hopping whatsoever. So the Majoranas that come in the expression will be paired as they are paired by the side they come. Pairings according to size. And the ground state of that Hamiltonian, sorry, maybe I said it, but maybe we will say something wrong. So at mu positive favors occupation, right? But now I wanted mu negative, so it favors emptiness, and indeed the ground state of this thing here is the vacuum in Fock space for this L chain. Okay, that was very clear in the first case, but it will help later to know where we are in this question. Now, this case is more limited. So we both have hopping and superconductivity, and for computational reasons, let's take them of the same states. Whereas the chemical potential shall be put into zero. And then what becomes of this expression? So you see here that this expression here, but now delta naught and W are the same. So the second zero, this first term is zero anyway. You're left with that one that is produced here. And here, if you look at which Majorana is paired with which other Majorana in this time, it's the gamma 2 here with the gamma 3 coming from the next side, and then second from the second side with the first from the third side, and so on and so forth, all the way to here. And so notice that among the Majoranas that appear here, the gamma 1 is absent, and so is the gamma 2L. They don't play a role. I mean, they are dynamical degrees of freedom, but they don't show up in the Hamiltonian. So the pairing now is across sides, as we call them. And we could revert to annihilation and creation operators, that notation, however, with new ones. So now this want to form a pair. So it's according to those that we revert to annihilation operator, but not the original one, and that's why they carry a tilde, according to the red grouping. And likewise for the adjoints. And then we may also take the leftover at the right end, and the gamma, and the gamma 1 at the left end, and also cook up some annihilation operator CL tilde on those. Notice that this operation is still a local operation. So, you know, it's no longer side by side, but it's still an operation that is done between neighboring sides. not mixing up things very distant, except for the last one. Their locality is somehow related, violated in my construction, because I take the Majorana from the far right and cook it up with the one on the far left. Okay, and then if you go back, if you were to write this, where is it, this in terms of this new Bayesian annihilation operators, you would get this expression here. And likewise, the Bayesian annihilation operators, they come to the Majorana ends are also absent in this time. So this means what? That now if W is positive as we want it, then we would like to now have emptiness for these J's, right? But with respect to the new writing, so I write for that omega L minus 1, because these are L minus 1 objects, not L as the length of the J. I put the tilde because they come from C tildes, and that's the new vacuum. So it's not the vacuum in the old sense. And then there is still the Fock space F1, which is just generated by this last CL tilde, the counterpart, and that's a C2. And there, since these do not appear in that Fock space here, I could pick any state I want, and that's still a ground state. So this means that the ground state is twofold degenerate, because this Fock space corresponding to this end Bayesian annihilation operator is two-dimensional. So by the way, this should also ring a bell. That in topological insulators, if they are topological, they are boundary state or edge states, if you count the thing. So this is signature of that. Of course, we should show that it's an insulator in the first place, and it shall be done. So what can we notice here? So any two psi's that you can use there are just boundary modifications of one another. They just differ in this C2 that models a degree of freedom at both boundaries. Each of the, so CL tilde, likewise CL tilde star, they change the fermion parity, because why? They were constructed from the gammas in the usual way, and the gamma changed the fermion parity. So the CL and CL dagger also change the CL star. I said dagger like a physicist, but it's star. Okay? And the two psi's could be chosen as a basis of that two-dimensional space here in such a way that they have different parts. So C acts on that space to itself and changes the parent. So if there is a state from one parent, there's also a state from another parent, and we can take them as eigenvectors of the parity of them. That would be the basis in that space. And here is the remark I anticipated. By bulk edge correspondence, this special case that we have looked at second, EE, belongs to a non-trivial topological case. Not so A, the thing before, which had no edge states at the end. Now, what is the BD? I'm heading to computing the bulk spectrum just to know, just to make sure it has the gap topological insulated wants to have. So what's the BDG Hamilton? So it's the general formalism is here, and the Hamiltonian is up there. So you see the C, for instance, the C dagger C goes with this psi. The C goes with this, I guess, goes with this delta star, and the C dagger goes with the delta or something like that. But so you can recognize what these things here. C goes with C dagger and C, actually in symmetric notation, where you C dagger C plus C dagger just absorb this one half of that. this gives this minus mu times the identity for sitting in. And then also this one has just CNC daggers, but it hops from left to right or from right to left. And so it's not difficult to convince oneself that if you call S the right shift on L2C, and therefore, you know, the left shift would be the transpose of the adjoint. It's the same thing in this case. This would correspond, this thing here would correspond to S star plus S. And that is all there is in sun. And the delta has, first it has to be anti-symmetric. So here you would just say there's also the shift, but you have to make it anti-symmetric. So subtract the transpose of it, that therefore means that you have a relative minus sign between S and S star of strength delta naught, and that is going to give you the delta. And the delta star is then the delta star. So we've identified psi and delta. Then by translation invariance, that's something we discussed earlier, it's not a context, but essentially still the same. You can use it to introduce quasi-momentum and the fiber of all Hamiltonians according to quasi-momentum. You start with the right shift. So if the right shift on wave function that quasi-periodic quasi-momentum k, it just acts as e to the minus k. And so you just introduce this into the psi and the delta to get the corresponding fibers, and then there you go. This essentially becomes a cosine, and this becomes a sine with a factor. If the volume of the Hamiltonian likely fibers like that. And you know, in this case, so this is 2 by 2, and the plots are really generated 1 by 1. And so the whole thing can be expressed as a linear combination of the 3 power layers. That's the best way to see what. So these 3 power layers suffice. And I write it like this: a vector E of k that dotted into the vector of Pauli matrices. And you realize that on the diagonal, that gives you this, the third component is the of psi. And on the off diagonal, you have something imaginary, purely imaginary. Therefore, you have no first component. You just have a second component, which is the vector. And the spectrum of that is quite easy to compute. So we can compute the bulk spectrum, and more precisely, we compute the spectrum of the overall loop of the Hamiltonian. We should call the corresponding eigenstates modes. The modes have energies, and in fact, a mode is a pair of the two plus and minus. And what is the energy of, what are the eigenvalues of such a linear combination of Pauli matrices? Well, I said it, it's that. And what is, how do we compute it? We compute it's delta squared plus absolute delta squared, right? And absolute size. And so that's that, and that's the form. Now you can ask whether this spectrum corresponds to the insulator or not. In particular, whether there is a spectral gap, and more in particular, spectral gap at equal zero. Because that's the position you would look for a spectral gap because of the top-down symmetry of the spectrum. So in order for that to be true, this energy E of k has to vanish no k. At no k, the gap closes. Then it doesn't close altogether. And let's go back to the two special cases we had before. One was where delta naught is equal to 0. Then this term here is absent. Second term here is absent. And then, you know, how does that work? You have a cosine that oscillates with an amplitude 2w, and you ask whether shifting it with mu, you intersect 0. And that can be answered pretty easily, that if the mu is large enough, then this won't happen. In fact, if absolute mu is larger than that, twice absolute w, then this won't happen. So here we draw a phase diagram with mu and w as coordinates, and if mu is in this situation here, that's the blue region here, and in particular, what did we use before? In the special case, W was 0 and mu was negative, so that is the special case we looked at before. So in this blue region, we have an insulator, because so the mu is, should I know this? So here is the cosine, right? And then you ask whether this we over the cosine A is equal to minus mu sum. So here is minus mu, and if it's like this, you have an intersection. But if minus mu is like that, you have no intersection. Since the width of this thing here is so this is a 2w, this is a minus 2w. See that if mu is outside of this range, this condition will not be satisfied. And therefore, you have a gap. Nowhere if E of k is going to be seen. So the blue region is an insulator. And an ordinary one, because if you cut the chain to the chain is infinite, but if you cut the chain to a finite one, no edge statement. And in the other case, where there the gap close, and so you have a net. That's the orange bit. But now let's get fancy. So there was no superconductivity here. Let's put it on. That's the delta naught parameter. And now the thing becomes more tricky. In order to get this equal to 0, before we just had this positive term, but now we have two positive terms. In order to get the whole thing 0, both terms have to be 0. And so I claim that at almost all mu and w, you have a gap, except, what does it take? So except when mu is equal to 2w in absolute value. And how come? Because a gap closure can occur only if also this term gets to 0. And that does occur at k equals 0 to pi. But then usually the first term is not 0, because then the cosine is either +1 or -1, and only that case it's also 0 if this condition. Then you have a gap closure, and the gap closure are these black lines, and everything else, everywhere else you have an insulator. So you have this blue region, which is an insulator, and we infer from the situation over there that we just make a slight positive delta. The gap, an open gap is a stable thing, so it will remain an insulator. But in the metal, a gap, in the metal, a gap opens, and the situation that we consider corresponded to what exactly? Corresponded to W equals delta and being positive. So that's this point here. And we recognize that provided it was an insulator, now we know it is topology. So the whole red region is a topology, stands for a topological phase. So that is the phase diagram of this entire chain. Yes, please.
What happens when we are around this transition with ordinary insulator and topological insulator on the line of water?
Then the gap closes. So
there is a phase there, or we cannot see. Because for example, when we speak of transition between metal and the ordinary barrier spec, there is something
exactly.
Yes. The case of ordinary topology.
Yes.
I don't know if I speak about some metallic things. So if there is something in the middle.
So it's the you already gave the answer. So I don't know whether this has a word, but it would be the analogon of a semi-metal or should. Now, why is semi-metal interesting? Probably because not just because there is a name for it, there are some properties. But I wouldn't know what the properties here are. And you know, this is sort of an exceptional point. What is really interesting in this red phase, where we have now the topological state, which actually should not be called the topological insulator, should be called the topological superconductor. Sorry. Yeah. Okay, so not so bad. So this thing, yes. So this now this is more general than just the slides. It's more general. What does it take to build a qubit? You know, it's easy to draw qubit. Oh, it's, you know, it's then you can see two, and you can have gates and manipulate it. But you know, what's the hardware for it? So this Kitaev chain or the things based on it are supposed to be possible hardware. So what does it take to build one qubit? It takes two states, like related to 0 and 1, you know, to get a serve at that qubit, and they have to be degenerate in energy. Why do they have to be degenerate in energy? Because if they have different energies, then just if you do nothing. So the nice thing is that you can do superposition. That's why you buy qubits. But if they have different energies and you just do nothing, then the superposition changes in the course of time. Because one if they have the 0 and the 1, if they have energies C0 and V1, and then you have alpha 0, 0 plus alpha 1, then in the course of time, this goes to V minus 0 plus alpha 1. And so, you know, if there is a certain superposition at the beginning, there's another superposition later on. Of course, you can say, oh, I go to the interaction picture and they get rid of that. But you know, to do that, we find that we have very precise control on 0 and V1, which is the challenge. So it's rather, it would be a lot better if they, for some reason, they had the same energy no matter what begins. They are the J. Then superpositions are stable in time. And also this degeneracy should be stable under generic perturbations. Now a system, you could never, the Hamiltonian in real life is never exactly the one you write down. So no, the degeneracy should not just be there for the one you write down. It should be stable under generic perturbation. And only, so on the other hand, you would be able to address the two qubits, the two states of the qubit in a different way. So only engineered perturbation, skillful manipulation, should be able to change the state, but not things that are just there in the parts. Oops. And so the question is, how does the Kitaev chain and the topological superconductors that has been constructed on how is it up to the task? So the two states you need are those of the edge. You remember that the edge in the topological phase provided the Hilbert space that is just C. And the states can be taken. So there are states in that state here of opposite fermionic parity. So first they have a definite and opposite fermionic parity, and they may serve as the state 0 and 1 of the qubit. And any generic perturbation preserves the fermionic parity. Now this needs some comment. That's the parity of charge. Not any genetic perturbation preserves the charge. Here's the reason. This device here is next to a superconductor, and charges can pass from one to one. So the charge that is contained in this red system is not conserved, but the idea is that only Cooper pairs can be exchanged between the red thing and the superconductor thing. So the charge, the fermionic parity is respected by the environment, and therefore it will not affect the states that you, the 0 and 1 that you use for grouping. Electrons come and go only as Cooper pairs, not one by one. So I mean, you have to make sure that this is true in order that this works. But you know, if it were not for the superconductivity property, the whole thing would be an insulator. So charges don't get in and out that easily, only as Cooper pairs they do, but that is fine. And hence, the perturbation is preserved the degeneracy, which is one of the things that you need to have the device working. And it preserves not only the degeneracy, but the two states, 0 and 1, individually, because they come with different fermionic parity, which is unaffected by the perturbation. That is the whole logic that is behind this proposal. No, and then you're still supposed to be able to address those qubits. But in order to address them, you have to act at the two ends of the chain simultaneously. Only then you can act on this edge state space. And nature would not do it by itself. It's only the engineer thing that can do. That's the idea. And so what is actually taking place in this business in experiment? In 2018, Carbon Hogan claimed to have such a system that I showed you with the semiconductor placed above the superconductor, where he could experimentally detect Majorana modes. And 3 years later, he had to retract the paper, because there was insufficient evidence that what he found were really Majorana setback and so on. But with Microsoft, who still bets on the technology, and now they have a machine they call Majorana 1, and they claim the realization of a quantum computer on that basis. If you follow the internet and YouTube, it's heavily contested. But we had at ETH a guy from this collaboration here who showed the result of that. They're quite impressive if you hear them. So, I said before that you cannot so what is preserved is fermionic parity. So in this device here, there might be, I don't know, 1 million electrons, just to say a number. Or there might be 1,000,002, and you cannot distinguish the two because these pairs come and go, or 1,000,004. But it's another situation to have just 1,000,001 or 1,000,003. And they can detect one parity from the other parity, even if there is 1,000,000 electrons in the system. So that's what they claim that they do, yes. But the thing is still very much contested. So that's what it's all about. With that, I essentially reached the end of this course. But before leaving, I wanted to leave you with one open thought. It has nothing to do with any particular thing I explained in this book, just the general topic. And this has something to do with the fractional quantum Hall effect. So in the fractional quantum Hall effect, they like to use effective field theories, and I thought, well, this is the place to say that. And the one that is involved for the fractional quantum Hall effect is Chern-Simons. And Duncan Haldane says, you can find it in talks and it's a probably to be person. Anyway, Chern-Simons theory takes the existence of incompressibility as given. So in other words, this gap we have been talking all along. Without this gap, nothing works. And Chern-Simons theory takes the existence of the gap of incompressibility as given and does not describe it. So the challenge is show the existence of the gap in a realistic microscopic model, not of the integer quantum model, of the fractional quantum model. That is a challenge. And if you are interested in picking up these challenges, you can go to the internet and find slides by Duncan Haldane. He has given essentially the same talks many, many times. You can also watch him on YouTube. And the title you have to look for is for the slides, geometry and incompressibility of fraction. Of course, mathematical physicists have thought about these things, and there has been some interesting work by Ingersoll and Rushby, which is, however, not exactly the real goal. It's called local incompressibility estimates for the last phase. And another thing, which I'm less certain that is up to the point, but I think it holds the promise, is by Kleptsov, geometry and large n limits in Loflitz. So, he addresses what happens for large n, which is in fact the regime where we want us. But all these three things are very different. In fact, the first one, Haldane himself, acknowledges. That was it.